So, hello everyone. In this lecture, we are going to study MATLAB application in control system. That is, we are continuing that topic which we have covered in the last lecture. So, in this lecture, we have seen we have to cover root locus and board plots, basically multiple plots, types of plots used in control system. So, the first one is root locus. The location of the closed loop pole in the S plane gives an idea about stability and transient response of a closed loop system. With a variation of any system parameter, those poles move from their locations. The knowledge about change in the location of pole is quite useful in the design of a closed loop system. To find out the location of the pole, the classical technique of factorization and the characteristic polynomial determines its root. However, if any system parameter is varied for adjustment, the characteristic equation change and computation have to be repeated to calculate the roots. The root locus technique introduced by W.R. Evan provide a simple graphical method of finding the roots of characteristic equation with a gain parameter k varying from minus infinite to infinite. There are so many conditions are there in root locus. The first important condition is angle condition, and second is magnitude condition. The magnitude condition says gs magnitude of GSHS should be equal to 1, and angle condition says angle of GSHS should be equal to plus minus 180 degree into 2k plus 1. It means it should be odd multiplication of 180 degree. So let's try to plot the root locus of any transfer function. We have a transfer function. So let's take an example. We have a transfer function. There are so many examples you can consider. So consider first example GSHS equal to k times s plus 2 and divided by 3s square plus 5s plus 7. Now we have to draw the root locus of this particular transfer function. So we can simply do it by using uh, R locus command. So first define the n matrix, which is, I think, numerator matrix of a transfer function, and D matrix, that is denominator matrix of the transfer function. So n should be equal to, I think the coefficient of s is 1 and for that of constant is 2. So this is n matrix, and now define D matrix equal to 3, 5 and 7. Now you can simply draw the root locus by writing R locus and passing these two parameters to this function n comma d. So this is the root locus of this particular transfer function, or you can modify this transfer function, this graph, by clicking on it, and you can check the particular value, that is frequency, overshoot and damping at this particular location. You can mark any of the. So I hope this root locus command is clear to you. Let's try to solve some other examples. Let's take another example, that is GSHS equal to KS plus 1 divided by S cube plus 10S square. We can draw its root locus by simply providing the n and d matrix to the r locus function. Let's try to code it. We can simply write r locus and directly pass these matrices. That is, first matrix is 1 1, and the denominator matrix is 1 10 0 and 0. When you hit enter, this will give you the root locus plot of this particular system. So this is the root locus plot of this particular system. I hope this how to draw the root locus of particular transfer function is clear to you. Let's try to do some other functions, or let's try to use root locus where you can get the value of k and r, where is the location of the roots and the value of k. You have to specify rk, root locus and d. So change this statement by simply putting r and k should be equal to this r locus. When you hit it, you can see there are multiple roots will be there, and there are values of k for which the roots are determined. These are the value of k, where k is varied from 0 to infinite, and this is the root location for this particular value of k, pole position basically. For the second example, you can see that these are the pole location for the value of k. So you can take another example. Let's take another example. I have considered n matrix as n equal to 1, and there is no zeros in the transfer function, and d equal to 3, 5 and 6. This is the D matrix, and when you solve it for roots R and the value of K, and you just plot R locus and pass these to N and D. This will give you K in the workspace. K is the gain, which varies from 0 to infinite. As you can see that the gain is varied from 0 and then further increasing till infinite. You can see here that at 53rd location infinite value of the gain is considered, and these are the roots position for the particular value of gain. And when you want to check the root locus plot, this is the root locus plot of this particular transfer function. I hope this root locus is clear to you. Now, if you have any system in the form of state space, you can also make root locus for such systems. So let's try to make root locus of a state space system. Let's take a system with matrix. Let me first clear this screen. Now let's take a system with dynamics as in the form of state space as x dot is equal to a matrix 0 1 0 0 0 1 minus 120 minus 40 and minus 10 multiplied with x plus 0 1 minus 10 multiplied with u, and the output is equation in a state space form as 1 0 0 multiplied with x plus 0 times of u. This is multiplication side. So we can find its root locus, or we can draw its root locus by simply generating all the matrices. First, let's take A equal to 0 1 0, then 0 0 1, the next row minus 120 minus 40 and minus 10. This will store in A. Now take B matrix equal to 0. This is for the first row. Then in the second row it is 1. Then it is minus 10. Now consider C matrix equal to, I think, 1 0 0. Similarly, D matrix should be equal to 0. Now you can draw its root locus plot by using rlocus command and passing all these matrices of the system A comma B comma C comma D. When you hit enter, this is the root locus plot of this particular system. And if you want to check roots and the value of gain k, you can simply write r k should be equal to r locus and passing all these matrices to this function, this will give you roots and position of and the value of k. The value of k, you can see here that it is varied from 0 to infinite. You can see here that all the values are listed. All the value of gain k are listed. And it is varied from 0 to infinite. Now the value of roots, these are the roots. This is at 0 position. When the value of gain k is 0, these are the roots, and so on. And this is for the last one is for the infinite. The value of gain k is infinite, then these three are the roots of the system. So I hope this root locus is clear to you. So the next is Bode plot. Bode plot are logarithmic plots. It has two graphs. One is the plot of logarithmic of magnitude of a sinusoidal transfer function, and the other is the plot of phase angle. Both plotted against the frequency on a logarithmic scale. The basic advantage of logarithmic representation is that multiplication and division operation of the pole zero representation of a transfer function can be replaced by addition and subtraction operation, and greater range of frequency can be considered. The frequency in logarithmic term can be represented as u log. U is the frequency in logarithmic scale. U equal to log 10 base omega. Omega is the frequency which you have to consider. So for plotting Bode diagram, the command can be used is Bode, or there is a function which is in the MATLAB, that is Bode, and you can find its Bode plot of any function. So let's try to solve some examples. Then you can simply get the Bode plot of any transfer function. So let's take some example and try to draw their Bode plot. Let's take example. The first one is A. We have taken 10 upon s square plus 7s. Second example we have considered is 10 upon s plus 1 s square plus 2s plus 5. Third, we have considered the example as s plus 6 upon s cube plus 5s plus 3. The fourth example, which is, let's take D as 7s upon s की power 4 plus 2s square plus 2s plus 3. So we have to draw the Bode plot of these transfer functions. So let's try to code it. So for the first transfer function we have considered, first clear all the variable in the workspace, clear the screen. Let's take n for the first transfer function equal to 10, and for d it is 1, 7, and the term constant term is 0. Now try to plot the Bode plot by simply writing command Bode, passing n comma d. When you hit enter, this will give you the Bode plot of this particular transfer function. This is the Bode plot of this particular transfer function. You can check the system frequency and magnitude at particular point. Here you can see that at this particular point frequency is 0.82 and magnitude is 4.75 dB. I hope this is clear to you. Here you can see that you can check the phase angle as well. Here the phase angle in degree is -141 and the frequency is 8.51 radian per second. So I hope this first example is clear to you. Let's try to code for the second one. Here we have to take n equal to coefficient for s is 10, and that for constant is also 10. Now d matrix, denominator matrix should be the value of s square is 1, for s it is 2, and for the constant it is 5. Now we can find its Bode plot by simply passing n comma d. So this is the Bode plot of this particular transfer function, and you can check the value of frequency and particular magnitude at this particular frequency. This is the phase angle and versus frequency plot. As you can see, you can mark on the graph for finding the value of phase and magnitude. Now let's try to code for the third one. For the third case, we have n equal to 1, 6, and d equal to 1, 0, 5, and 3. Now you can draw its Bode by simply passing n comma d. This is the Bode plot for this particular transfer function. I hope this is clear to you. Now let's try to code for the last transfer function. So first clear the screen, clear the command window as well, clear workspace. So n equal to 7, 0, and d equal to all the coefficient of denominator, that is 1, 0, 2, 2 and 3. Now you can simply draw its Bode by passing these two matrices to the Bode function. When you hit enter, this will give you the Bode plot of this particular system. I hope this Bode plot is clear to you. Now you can also find gain margin, phase margin, and gain crossover frequency and phase crossover frequency for particular system by simply writing. Let's try to find out for this particular system by simply writing a function that is margin and passing these two matrices n and d. So when you see that it is this is the point where there is a gain margin at particular phase crossover frequency. So the gain magnitude is minus 0.0459 and the frequency is 0.401 radian per second, and this particular frequency is basically phase crossover frequency, and this is, as you can see, gm is infinite as magnitude is nearly equivalent to 0. So when you divide it using 1 upon x form, it will give you the value of infinite, and pm is 107. As you can see here that at this particular point phase angle is minus 180 280, and when you have to find the value of phase margin, you have to add the 180 degree. When you add 180 degree, it will give you minus 107, and the frequency is 0.041 radian per second, which is nearly equivalent to 0.403. I hope this is clear to you. Let's try to find for another a transfer function. Let's take the C as a transfer function and try to find the margins. First I clear the workspace and then clear the screen. So let's take C as an example. You have to pass n equal to 1 and 6. In a similar way, you have to pass d equal to 1. The square term is 0, so consider the coefficient as 0, 5, 3. When you hit enter, this will give you D matrix, and just pass it to margin n comma D. As you can see here that gm is infinite. It is written there at infinite radian per second, and pm is minus 93.1 degree. Here this is pm. You have to subtract 180 from this or add 180 degree to this at 2.68. So my location is wrong. Just put here. This location is also wrong. So this is the particular location where the frequency is 2.68 2.69 radian per second, and phase angle is minus 273 degrees. So I hope this margin is clear to you. Margin concept, or that is, we have to find the different uh, position of, that is the different values of gain margin, different a parameter of a board plot, that is gain margin, phase margin, gain crossover frequency, and phase crossover frequency. All these are defined on the top of the graph. That is, gain margin is infinite at infinite radian per second, and phase margin is minus 93.1 degree at 2.68 radian per second. I hope this Bode plot is clear to you, and how to find the gain margin and phase margin. I think this is one of the simplest topic in MATLAB. So moving ahead to the next topic, that is Bode diagram for state space representation. So I will give you one example. Consider a system with state space representation as x1 dot x2 dot equal to zero 1 minus 20 minus 2 state x1 x2 plus 0 20 u, and the corresponding output for the system y equal to 1 0 x1 x2. So this is very simple, and you can simply code it. Just let's try to code it. So matrix A can be written as A equal to, let's clear first and then CLC. So A matrix is A equal to 0 1, and for the second row it is minus 20 minus 2, and the B matrix is equal to 0 slash 20. Similarly, C matrix is equal to 1 0, and D matrix is equal to, as it is not given but you have to define the D matrix, which is 0. Now you can simply draw its Bode by passing all these matrices A, comma B, comma C, comma D. Now when you hit enter, this will give you the board diagram for this particular system. You can take any other example as well. I hope this is clear to you, and this is very simple and easy to make board as well as root locus of any transfer function which you have given. You can draw its board plot as well as root locus for particular system. The next topic is Nyquist plot. The Nyquist plot is a plot of magnitude of a particular system versus angle gj omega for the frequency range. For the frequency is varied from minus infinite to infinite. Nyquist plot and Nyquist stability criteria is useful for determining the stability of the closed loop system from the open loop frequency response without determining the closed loop poles. The stability of the closed loop system is determined by finding out the number of encirclement around -1 plus j0 point by the Nyquist contour of the open loop frequency response. So let's take some example and try to draw the Nyquist plot of a particular system. So let's take two examples. Let me draw first the box. So this is the example first is A. Try to draw the board plot of, Nyquist plot of 1 upon s square plus s plus 1. Second example B is s plus 2 upon s minus 1 or s square minus 1. Third example C is 1 upon s square minus 2s plus 3. Let's try to make the Nyquist plot for these examples. First clear the screen as well as clear the workspace. So here define n equal to 1, d equal to 1, 1 and 1. So we have a function that is Nyquist and passing these two matrices n comma d. And this will give you the plot of Nyquist plot of this particular system. As you can see that this is the Nyquist plot or Nyquist diagram for the system. You can see that it is the value you can find out for particular frequency, the real and imaginary value you have find out for the particular frequency when you click to the particular point of the plot. Let's try to code for the second one. For the second one, n equal to 1 comma 2 or 1 2 and the d is 1 0 and -1 Just write nyquist and pass these two matrices will give you the nyquist plot for this particular system. I hope this is clear to you. Let's try to code for the second one, or the sorry, last one. So take n equal to, that is numerator matrix equal to 1, d matrix equal to, that is 1 minus 2 and 3. Let's try to make it nyquist plot. You have to write nyquist and pass these two matrices n comma d. When you hit enter, this will give you the nyquist of this particular system. So I hope nyquist plot is clear to you. In the similar way, you can find the Nicole chart of any particular system. Basically, Nicole chart is the constant magnitude loci, that is n circle, and constant phase angle loci, that is n circle, when transferred to log magnitude versus phase plot are called Nicholas chart. Thus, Nicholas chart is a graph consisting of curves that are maps of m and n circles on a new coordinate system, that is m and n loci in dB magnitude versus phase plane. The Nicole coordinate system has open loop gain in decibel on y-axis and phase angle in degrees on x-axis, with origin at magnitude of g equal to 0 dB and angle of g is equal to minus 180 degree. So let's try to uh, draw the Nicole chart for these particular systems. Try to code for the first one. For the first system, we have defined n equal to n equal to 1 and d equal to 1, 1 and 1. So we have a particular function, that is Nichols, to draw the m and n circles, and we have to pass this function with n comma d. When you hit enter, this is the Nicole chart for this particular system. As you can see, this is open loop gain in dB and open loop phase in degrees. These are the axes for particular system, and you can on the grid, and you click grid, this will give you the grids on this particular chart. Now let's try to code for the second one. Here we have n equal to 1 2 and d equal to 1 0 and -1. When you pass it to the function Nichols, n comma d will give you the Nicholas chart for this particular system. Make grids on will give you this flow. Let's try to code for the third system. Here you can see that n equal to 1 and d equal to 1 -2 3. And you can simply draw Nichols chart by passing n comma d. Just make grids on by simply writing grid will give you the Nichols chart for this particular system. I hope how to draw Bode plot, root locus, Nyquist plot and Nichols chart is clear to you. You can simply draw for the particular state space system by simply passing all the matrices A, B, C and D. So I hope this is clear to you all, and thank you very much for patiently listening.